Alright, hello class. In this video we're going to be talking about implicit differentiation. And this is sort of a continuation of the chain rule, because now that we have the chain rule, that opens up the possibilities almost endlessly as far as like what kind of functions we can tackle, what kind of expressions we can tackle. In fact, we don't even have to differentiate functions as we know them traditionally, right? Because so far, everything we've pretty much looked at has been a y equals some f of x, right? And so when we differentiate, our dy by dx is going to just be, say, f prime of x, right? However, there are way more things out there. Okay, so this is what's called an explicit function or explicit expression. Okay, but there are many things out there that don't break down into a nice function that we're used to. So for example, think of the unit circle. All right, so here the unit circle, this is not a traditional function because it fails the vertical line test, right? In fact, the formula for the unit circle is x squared plus y squared is equal to 1. This is what's considered an implicit formula. In other words, explicit means that we can solve it for y all the way down, whereas implicit means that y is part of the formula itself. So in math speak, it's explicit is this, y equals f of x, okay, so that's explicit. Okay, implicit is more like this, capital F of x, y equals 0. So that's implicit. So that means y can be in the part of the formula as well as y squared, x squared, y cubed, etc. Okay, so in this particular case, our capital F of xy, okay, would be x squared plus y squared minus 1, because we're setting it equal to 0 to be an implicit formula. Okay? But in this case, with the unit circle, what we can do is we can actually solve for y. So move this over, that y squared is equal to 1 minus x squared. Right? And so y is equal to plus or minus the square root of 1 minus x squared. So what ends up happening is we have two separate functions. The top half of the circle, okay, is given to us by the plus square root of 1 minus x squared. And the bottom half is given to us by the minus. Okay. All right, so from here, if we wanted to find, say, the slope of any tangent line, if we wanted it on the top half of the circle, we would have to use this form, right? This version, the plus square root. But if we wanted, say, a tangent line slope down here, we would have to use this one in the blue. All right, so we would have two derivatives that we would have to calculate to do this. All right, so for the one in the red, it would be a plus square root of stuff. So this would be plus the derivative of the stuff, which would be minus 2x all over 2 times the stuff, or the square root of the stuff, so that the 2's cancel. So we end up with negative x over the square root of 1 minus x squared. And we would do this work again for the one in blue. So dy dx, it starts with a negative, but otherwise the derivative will be the same. It'll be a negative 2x over 2 square root of 1 minus x squared. The 2's cancel, and the minuses cancel. So we actually get a plus x over the square root of 1 minus x squared. Okay, so if we want any point down here in the blue, we have to use this blue derivative, and if we want to find anything up in the red, we need to use this red derivative. So let's do that. Let's find the slope of the tangent line, let's say at the point up here. Let's say at the point root 2 over 2 comma root 2 over 2. And then we'll do, say here, this would be, let's say it's 1/2 comma negative root 3 over 2. I'm just taking angles for 45 degrees and negative 60. All right, so I'll clean this up a little bit. The derivative of y with respect to x here in the red, when x is equal to root 2 over 2, is going to be negative root 2 over 2 all over the square root of 1 minus root 2 over 2 squared. Okay, so that's going to be negative root 2 over 2 all over, well, when we square root 2 over 2, it's going to be 2 over 4, which ends up being 1/2. Okay, so it ends up being 1 minus 1/2 underneath the square root. So it's actually negative root 2 over 2 all over the square root of 1/2, which we could rewrite as 1 over the square root of 2. And the reason I'm going to leave it like that is because when we invert and multiply, we're going to get negative root 2 over 2 times root 2 over 1. The two root 2's come together to be 2, so we get negative 1. Okay, so that is what we calculated to be the slope of the tangent line here. And that actually holds some water. That looks right, that the slope should be negative 1. All right, so now we're going to find the slope of the tangent line here. Now notice we need to use the blue one to do this. So for the blue derivative, dy over dx, when x is equal to 1/2, well, thankfully this is going to be a little nicer because we're not dealing with all these square roots. This is going to be 1/2 all over the square root of 1 minus 1/2 squared. Okay, so we'll get 1/2 all over the square root of 1 minus 1/4. All right, so this is going to be 1/2 over the square root of 3/4, or 1/2 over root 3 over 2, and then we'll invert and multiply to get 1/2 times 2 over root 3, and we get 1 over root 3. Okay, which is also, when we rationalize the denominator, it should be root 3 over 3. Okay, so we do get a positive slope here, and a pretty shallow one compared to this one up here. So that also holds some water. Now, we'll notice here that this is a little messy, right? We have to know which half of the circle we're working with. Okay, now, that's one sort of disadvantage of doing it this way. Another is that we might not always be able to solve for y. Okay, if we're not able to solve for y, we're kind of stuck. So here's another thing we can do, and that's implicit differentiation. Okay, so a more efficient way to approach this is implicit differentiation. And this is where we leave the formula in implicit form and then treat each y as a function of x. In fact, we are assuming that y depends on x, yet is trapped in this implicit formula. Okay? Then we differentiate, treating y as a function of x. So in other words, we use the chain rule anytime a y derivative shows up. Okay, so this is one of those situations where it's difficult to describe in words, so it's much better to just do it with an example. Okay, so what we're going to use this with is the unit circle that we were just looking at. All right, so here's our unit circle here. This x squared plus y squared is equal to 1. And for implicit differentiation purposes, we are going to consider this y squared as a y of x squared. All right, so when we go to differentiate this, we're going to be using the chain rule here. All right, so now I want to differentiate this with respect to x. All right, and I hope you all don't mind. I'm going to start using diff as an abbreviation for differentiation and WRT for with respect to. Okay, we're going to use with respect to a lot, so that's going to save us a little time. So what we're going to do is basically differentiate with respect to x everything. So we're going to take x squared and differentiate it with respect to x. Differentiate this y of x squared with respect to x. And finally, we're going to differentiate 1 with respect to x. Okay, so the derivative with respect to x of x squared, of course, is just 2x. No problems there. Here, though, this we need to use the chain rule. So this is where the chain rule shows up, because it's y of x squared. So this is going to be 2 times y of x to the 1 times y prime of x. Okay, so this is where the chain rule comes in. And then the derivative of 1 is, of course, 0. So now what we do is when we get to this piece, we're going to solve for y prime. All right, so to do that, I'm going to move everything with a y prime on one side and everything else without to the other. Okay, so I know students, not all students, but some students have trouble with this when they're first learning it. Just think of the y prime or the dy dx as an x and everything else is numbers, and you're just trying to solve for this thing here. Okay, so we're solving for this, meaning we need to move this over, and then we're going to divide by this once we do it. Okay, so we're going to get 2 y of x times y prime of x is equal to negative 2x. Okay, now we can divide by this whole thing here. All right, so we'll get y prime of x is equal to negative 2x over 2 y of x. Okay, the 2's will cancel and we get negative x over 2 y of x. And if we want to simplify the way this looks a little bit, we can say that y prime is equal to negative x. Whoops, that 2 should be gone. Sorry about that. So what we get at the end is negative x over y, which is actually pretty interesting if you think about what we saw before. In both cases, we got a negative x over y because, well, in the blue case, it was y was negative square root of this thing, so the negatives canceled. And here in the red, y was the plus square root of the thing. So in both cases, right? In both cases, this was y, and this was y. So we ended up, at least here, we ended up getting negative x over y in both situations. That's one of the advantages of implicit differentiation. We get a nice formula that we can utilize no matter where we are, as long as we put the right point in. For example, if I want to find y prime at the point root 2 over 2, root 2 over 2, okay, it's just going to be negative root 2 over 2 all over root 2 over 2, which is negative 1, which is exactly what we got in the previous way of doing this at this point. The difference is we have to plug in both the x and the y when we do it this way, but this to me is much, much faster than how we were doing it before. All right, so not only is this method more efficient in certain cases, in others, it's likely the only way to do it. So for example, if we have x plus y cubed minus xy equals 1, trying to solve this for y is not going to be a good use of our time. Even if we can do it by hand, it's really not worth it. And especially if we look at what the graph of this looks like, all right, when we graph it, we get this strange looking curve. My software is kind of messing up here, which is kind of normal for these guys, or it can be. But essentially, if we were to solve for y, we would get 3 solutions. Essentially, we'd get y equals 1 as one of our functions. We'd get some sort of y equals the square root of something, and negative the square root of something, right? So we got a parabola and a line. And then if we did this, in order to find sort of the slope of the tangent line at any particular point, we would have to pick the right one of those pieces. Okay, so instead what we can do is just use implicit differentiation and then plug in the point in terms of x, y to get the right value. So implicit differentiation will give us the correct value. So if we plug in 7, 2, it knows, just through the technique of it, that that's what we will get here. Or if we plug in 7, 3, 3, 1 would be an interesting problem here, because this is where we get sort of an intersection, right? So what we'll probably find is something very bizarre happening here at 3, 1. So let's give it a shot. All right, so we're going to go about differentiating this with respect to x. So in order to do this, I'm not going to write y of x every time. However, I'm going to replace y with a different color here, just to show that, okay, it's x plus y cubed, which is a function of x, minus x, and then it's times y equals 1. Okay, so when we go to differentiate each piece here, okay, we'll get this. All I've done is, well, apply the derivative to each piece. Okay, this isn't necessarily a step you have to write, but early on here, while we're still getting to grips with this, it doesn't hurt. Okay, all right, so we're going to have the derivative of x, which is just 1, plus the derivative of y cubed. But remember, y is a function of x here, so we need to use the chain rule. So it's going to be 3 times y squared, right, then times y prime, or times dy dx. Okay, this is often how you see it written out, but you could put a y prime as long as you don't get it mixed up with, say, a y squared or y cubed or what have you. But we tend to write it like this, so it's very clear that we are talking about a derivative and not, say, y to the 1, which, you know, you could mistake for that. Now here, when we go to differentiate x times y, this is going to be a product rule. Okay, so it will be, let me be careful with my parentheses here. All right, it'll be the derivative of the first guy. Well, that's just x, so that'll be 1 times y left alone. Okay, then plus, well, the first guy left alone, now times the derivative of the second. Well, the derivative is second, just y. Its derivative is going to be dy dx. Okay, and then equals the derivative of 1, which is just 0. Okay, so let's simplify this a little bit. This is 1 plus 3y squared dy dx. I'm going to distribute this negative sign, so I have negative y minus x times dy dx equals 0. Okay, and we're going to solve for what's in pink here. Okay, the dy dx. So again, like I've said, some people have trouble with this when they're first learning it, and it's understandable. This is very different than what we've done before, but just keep in mind we were just solving for the dy dx. So that means we're going to move everything that isn't a dy dx, so the 1 and the negative y over, factor and divide. Okay, so let's move these guys over. So we have 3y squared. Oops. Okay, we have 3y squared dy dx. We have minus x dy dx is equal to, all right, we move the y over to get a plus y and the 1 over to get a minus 1. Okay, so we move these two guys over. We keep these guys on this side. Okay, and now we will factor out that dy dx. Okay, since these two terms share it. So we will get a dy dx times what's left, which is this 3y squared minus x equals y minus 1. And now we can just divide by this whole thing. Okay, so we get dy dx is equal to y minus 1 all over 3y squared minus x. All right, so here we have the derivative of this implicit function. If you want to remember what it looks like, it's this sort of funky looking guy here. And now I'm going to check it at some of those points that we mentioned. So one good one and a fairly easy one would be the point 1, 0. And then we could also check it at 7, 2 and 7, negative 3. And then I also want to take a look at what's happening at 3, 1 to see what sort of weirdness might be going on there. Okay, so we're going to find the slope of the tangent lines at 1, 0, 7, 2, 7, negative 3. I added 2, 1 in, so here's 2, 1 right here, just to show that it's going to line up with that horizontal line there. And finally at 3, 1. All right, so there's quite a few points here, so we're just going to kind of drive through them real quick. All right, and I want to mention, if you're unfamiliar with this notation here, this big bar, this is basically saying we're plugging the 0.10 into the derivative. Or here, plugging the 0.10 into y minus 1 all over 3y squared minus x. Okay, so here at 1, 0, we're going to get, well, x is 0, or x is 1, y is 0, so we'll get 0 minus 1 all over 0 minus 1. So it will be negative 1 over negative 1, which is 1. All right, and when we go back to the graph, I just made the tangent line with slope 1 here. And yes, that does line up pretty much exactly. Okay. Okay, for 7, 2, of course, we're going to get 2 minus 1 all over 3 times 2 squared minus 7, okay, which ends up being 1/5. All right, when we plug in 7, negative 3 into the derivative formula, we'll get negative 3 minus 1 all over 3 times negative 3 squared minus 7, which comes out to be negative 4 over 20, which is negative 1/5. Now, if we go to the graph, okay, here on the graph at 7, 2, we got 1/5, and at 7, negative 3, negative 1/5. Now, we can see that these, at least here, the parabola, these should line up, and that's kind of what we got. If we graph the tangent lines real quick, okay, as you can see here, for the tangent lines, they essentially match. We get the 1/5 and the negative 1/5. Right, next up, we're going to evaluate the derivative at the point 2, 1. So y is 1, so you get 1 minus 1 over 3 times 1 squared minus 2. So we end up with 0 over, this will be 3 minus 1, which is 1. So that's 0. Well, that's exactly what we have here on the graph. Let me get rid of these. 2, 1, well, the line is constant. All right, the graph is constant here at 2, 1. So we should get 0. In fact, any point along here, we should get 0, except maybe at 3, 1. So let's see what's happening at 3, 1. All right, so now evaluating this derivative at 3, 1, we'll get 1 minus 1 up top, then 3 times 1 squared minus 3. So this ends up being 0 over 0, so it's undefined, right? And what happens there, or specifically why it's undefined, it's not really a case where we could say take the limit, because there's not really much we can do sort of regarding this. But again, this is on the graph where this is where these two lines sort of intersect. So what's happening is if we are approaching it along this line here, this horizontal line, we'll be getting 0, but if we approach it along this parabola, we'll be getting something positive. So whenever you see intersections like this in a graph, you should end up with some sort of 0 over 0 or some sort of undefined behavior, right? Because the formula doesn't know which one you're talking about. Okay, if you were able to split it up into two separate pieces, you could talk about which particular function, but again, this is an implicit curve, so the graph is this whole funky thing here. All right, from here, we're just going to look at some more examples of implicit differentiation. All right, so for all these, we're just going to find dy dx. We're not going to worry that much about plugging things in necessarily, but I think this is one of those cases where it's more beneficial to just look at a bunch of examples. So that's exactly what we're going to do. Just look at a bunch of examples. So if I want to find dy dx implicitly, okay, when we have y is equal to x e to the y, well, again, we are going to use the chain rule whenever we see a y. Okay, so on this side, it's not that big of a deal. Dy dx is literally just dy dx. Okay, the derivative of x with, or the derivative of y with respect to x is the derivative of y with respect to x. However, on this side, okay, what we have is actually a product rule because this is x e to the y. Okay, so when we differentiate both sides like this, well, the left side is going to be just dy dx. Okay, but on the right side, we have to do the product rule. All right, so it will be the derivative of the first guy, which is x, so that'll be 1 times e to the y. Okay, then plus the first guy left alone, then times the derivative of the second. Well, the derivative of the second is going to be itself, it's e to the y times the derivative of the stuff, which is y. So anytime we do a y derivative, we need to throw in a dy dx. Okay? All right, if we simplify this a little bit now, we have dy, actually let me use the other color here, we have dy dx is equal to e to the y plus x e to the y dy dx. Okay, and now we're going to solve for dy dx. Okay, so we're going to a lot of ways we could do this, but I'm just going to move this over. All right, so that we get dy dx, okay, minus xy, or x e to the y, dy dx, is equal to e to the y. Okay. Now we can factor out the dy dx, and again, the more you do this, the more you will start to get comfortable with the fact that you're always factoring out the dy dx. So a lot of times people will skip right to this, 1 minus x e to the y is equal to e to the y. Okay, just don't forget that 1. And then we'll divide both sides by this to get that dy dx, okay, is equal to e to the y all over 1 minus x e to the y, and there we go. Once we get that dy dx solved for, we're done. All right, let's look at another example here. Let's say we have x plus 2y is equal to the square root of y. All right, so we will just differentiate every piece here. Okay. And just go through it piece by piece. Now again, eventually I'm going to start, or I guess more accurately, I'm going to stop writing the d dx every single time. But this is where we're going to get from step 1 to step 2 when we start doing that. Anyway, the derivative of x is 1. The derivative of 2y is going to be 2 dy dx. So remember, you always just differentiate like normal, but you're applying the chain rule. And then dy dx of the square root of y, well, remember your chain rule is going to be dy dx all over 2 square root y. Okay, now we want to solve for the dy dx. Now, before we do that, I'm going to multiply this 2 square root y over so we don't have that fraction anymore. Okay, so multiply that over so we get 2 square root y plus 4 square root y. Dy dx is equal to dy over dx. Okay, so now we'll move this 4 root y dy dx over to get 2 root y is equal to dy dx minus 4 root y dy dx, and now we can factor that dy dx out. So I'll go ahead and continue this chain of equal signs here to get dy dx times 1 minus 4 root y. All right, and then we can just divide everything by this to get 2 root y over 1 minus 4 root y is equal to dy over dx. Okay, and there we go. All right, so I wanted to show the graph of this particular function just to kind of show like how weird some of this stuff can be. Here we, hang on, there we go. So this function sort of behaves in this sort of way. It goes all the way to 0, 0. But what I wanted to show is the nice thing about this implicit differentiation thing is if we consider it, say, at this point here, right? So this is the point 1/8, comma 1/16, right? So this is 1/8, comma 1/16. So if we plug that into our derivative, okay, we would get 2 times the square root of 1 over 16, right? All over 1 minus 4 times the square root of 1 over 16. So this is going to be 2 times that will be 1/4 all over 1 minus 4 times 1/4. So we get, this will be 1/2 over 0. Okay, this is an undefined tangent line slope, right? This is an undefined slope. However, this is where we have a vertical tangent line, right? If we look back at the graph here, at this point, our tangent line is vertical. It's a constant over 0. In other words, that's an infinite, right? The constant over 0 is a plus or minus infinity. That's a vertical tangent line. I totally misspelled vertical there, but yeah, so this can actually show you where we have vertical tangent lines, because it's whenever the denominator is equal to 0, but the numerator is not. So remember, in the previous example, we had a 0 over 0, right? So that 0 over 0 was basically where the graph intersected, okay? But here we got a constant over 0, and that was where we ended up with a vertical tangent line. Okay, so this method can show us where we have vertical tangent lines or intersecting tangent lines. Anytime any weirdness is happening here, there's weirdness happening on the graph as well. All right, next up, let's look at sine of xy is equal to x plus y. So I wanted to show, this is how the book would write this. This is how I would write this. I would say sine of x times y is equal to x plus y. So this here is going to be a chain rule with a product rule on the inside. All right, so when you go to differentiate everything, well, the derivative of sine of stuff is cosine of that stuff, left alone, then times the derivative of the stuff. And when we go to do the derivative of the stuff, that's when we do the product rule. But this product rule is also going to have a y, so it's going to end up with that y prime showing up with the dy dx. So be the derivative of the first guy, 1, times the second guy left alone, plus the first guy left alone, times the derivative of y, which in this case is dy over dx. Okay. So we differentiated the left-hand side of the equation, so now we're going to go to the right-hand side. So derivative of x is 1. The derivative of just y all by itself is dy dx. Okay. So here was the product rule. And now we're left, let me clean this up a little bit, we're left with cosine xy times y plus x dy dx, okay, is equal to 1 plus dy dx. Now, to solve this one, we need to distribute this cosine of stuff across, okay? And I'm going to kind of rewrite things so the cosine goes behind. So we're going to have y cosine of xy plus, let me do it this way, dy dx times x, okay, I don't know why I'm having trouble there, x cosine of xy is equal to, and this side didn't really change. Okay, and so now we're going to solve for the dy dx. So we need to move everything with the dy dx over to one side, everything without to the other. So what I'm going to do is move this piece over this way, and then this piece over to this side. Okay, it doesn't really matter in the end. So we'll have dy dx times x cosine xy, okay, minus dy dx, okay, which is equal to, now 1 minus y cosine of xy. All right, now we can factor out this dy dx and divide. So when we factor, we'll get x cosine of xy minus 1 is equal to 1 minus y cosine of xy. And then we'll just divide both sides to get dy over dx is equal to 1 minus y cosine of xy all over x cosine xy minus 1. Whew! All right, there we go. There's the derivative using implicit differentiation. All right, here's another example. Cosine of y squared plus x equals e to the y. Again, this is how the book would write it. This is how I would write it. I would put parentheses around the input. I think book publishers try to save as much ink as they possibly can, so they aren't very diligent about making it easier on students. But again, once you get more comfortable with it, it maybe becomes a little second nature. But anyway, this is going to be basically two chain rules. All right? So when we differentiate this, the derivative of cosine is negative sine of the stuff, and times the derivative of the stuff. Well, the derivative of the stuff is stuff squared. It's going to be 2y dy dx. Okay. Then that plus x will become a plus 1. And then this e to the y, well, since we're differentiating with a y in it, it's going to be e to the y times dy dx. Okay. So I'm going to move the e to the y over and the 1 over here. Okay. So we're going to get, I'm going to say negative sine of y squared times 2y times dy dx minus e to the y dy dx is equal to a negative 1. Okay. Actually, it might be easier to move the sign over, but now that we've already done it, it doesn't matter. But I'm going to take out a negative dy dx. So that'll be left with sine of y squared, 2y. So let me write it like this instead, so it looks a little nicer. 2y sine of y squared plus e to the y. And the reason I factored out a negative dy dx is because we can start by dividing out the negative 1, right? Essentially to get rid of the negative, and then divide through by this thing. Okay. Now, you don't have to do that. It's just my own sort of thing I want to do here. But so our final answer here, dy over dx, will be 2y sine of y squared plus e to the y, all under a 1. And there we go. All right, for our next example, let's look at y is equal to x plus 1 all over y minus 1. Now, I think a lot of people, when they first see this, will go straight to just differentiating everything, right? Which you can. The only thing is here, if you do, say, dy dx on this side, that's not too bad. But then on this side, you have to use the quotient rule. And so for the quotient rule, well, that'll be the derivative of the top, which is just 1, times the bottom left alone, minus the top left alone, times the derivative of the bottom, dy dx, all over the bottom squared. Okay, and then you have to solve for dy dx in all of this. Now, it maybe isn't the most difficult thing to do. You can move that y minus 1 squared over to get y minus 1 squared dy over dx is equal to y minus 1 minus x plus 1 dy dx. And then we can solve like normal. Move this whole thing over to this side to get y minus 1 squared dy dx plus x plus 1 dy dx is equal to y minus 1. We factor out the dy dx, being very careful about how we write things. So we'll have y minus 1 squared plus x plus 1 is equal to y minus 1, and then we can divide the whole thing over. So that dy dx is equal to y minus 1 all over y minus 1 squared plus x plus 1. And there we go.
All right, there's nothing wrong with doing it this way. However, I would argue that we would have a much easier time if, once we started, we moved this y minus 1 to the other side. Can we do that? Well, turns out we can, because if I multiply this over to get y times y minus 1 is equal to x plus 1, we'll get y squared minus y on this side and x plus 1 on this side. This is going to be a much easier thing to differentiate. Now, when we do this, we have to keep in mind that we are taking a look at a different curve. We have to keep in mind that this one, originally, y is not allowed to equal 1. Okay, so we can look at this curve instead and say that, well, y is just not allowed to equal 1. Okay, so showing you on a graph what's going on, here is our original. I moved, in order to do this in a software, you have to kind of move everything over to one side. So this is y minus x plus 1 over y minus 1 equals 0. It's really the same thing. So notice we have this sort of parabola, and it's having trouble graphing around y equals 1. That makes sense. There's a hole there. Okay. Now, here's, again, it sort of moved things around. It moved the x over and what have you. But here's the other equation, and you'll notice it's the same thing, except it doesn't have that hole there. But we have to remember that there's a hole there. So yes, we can instead look at this curve and find the derivative, just keeping in mind that y is not allowed to equal 1. Okay, doing it this way, well, now we can just differentiate everything. So we'll have 2y dy dx minus dy dx, which will be equal to 1 plus 0 when we differentiate everything. And look at this, all the dy dx's are already on the same side, so we can just factor to get 2y minus 1 dy dx is equal to 1. And we just divide through. Dy over dx is equal to 1 over 2y minus 1. All right, 1 over 2y minus 1. Now, your initial response may be, well, are these the same thing? Well, that takes a little bit of work to show. All right, but it turns out with a little algebra, we can actually show that these are the same. What we're going to do is, with this one in the blue, in the denominator, I'm going to actually factor out a y minus 1, and we're going to do so in the way I talked about before, where if you factor out a y minus 1, well, in this first piece, we're left with just a y minus 1, and in the second piece, well, we're going to divide the x plus 1 by y minus 1. And here the y minus 1's cancel. Okay, and we're left with 1 over y minus 1 plus, well, x plus 1 all over y minus 1. That's what y is equal to. So this piece right here is actually equal to y. All right, so then this comes out to be 1 over, well, 2y minus 1, which is exactly what we got over here. Okay, so while they might not look like it initially, they do end up being the same thing. Okay, so we can actually do this. So always be on the lookout for things that can actually simplify your life as we go through this. I'll show another one in the next example.
All right, so for this example here, let's say we have the square root of x plus y squared is equal to sine of y. Now again, this is one where we could go straight for it, right, and start differentiating. So remember, the derivative of the square root of stuff is the derivative of that stuff. So in this case, 1 plus
2y dy by dx all over 2 times the square root of the stuff. Okay. And then we'll differentiate this side, so the derivative of sine of y is cosine of y times dy dx. So let me put that on out front instead. So that we have dy dx cosine y. Okay, and then we have this wonderful equation to solve. Essentially, we would move this, I would start by moving this denominator over to get 1 plus 2y. Dy dx is equal to dy dx times 2 square root of x plus y squared times cosine y. All right, and then I would just move this guy over so that I had 1 is equal to dy over dx. I'll go ahead and factor and move at the same time. So I have 2 square root of x plus y squared cosine y minus 2y. And that's what we would go ahead and divide by. So dy by dx will be 1 over all this junk here. The 2 root x plus y squared times cosine y minus 2y. All right, but another way we could go about doing this is instead of leaving it with a square root, we could square both sides. Now we do have to be careful when we do that because we can introduce some inconsistencies, we can introduce some redundant solutions or things that don't work. But if we square both sides, we will get x plus y squared is equal to sine y squared. Okay, and if we then start differentiating, we'll get 1 plus 2y dy dx. And on this side, it's a chain rule within a chain rule. Right? It's going to be 2 times sine y raised to the 1, then times the derivative of sine y, which will be cosine y, then times dy dx. Okay, so once again, let me split this off here. I'll move this 2y dy dx over so that we get 1 is equal to, and once again, I'll go ahead and factor and move at the same time. So we have dy dx times, it'll be 2 sine y cosine y minus 2y. All right, and then we'll divide so that we get dy over dx is equal to 1 over 2 sine y cosine y minus 2y. Now, are these two the same? Well, they look similar. In fact, they look way more similar than what we saw before, and it turns out yes, because what does this square root of x plus y squared equal? Sine y. This is sine y. So all we would have to do to get this derivative to look like this one is replace this root x plus y squared with sine of y. And we can actually simplify this a little further if we wanted. There's not really a need, but sine of 2y is actually 2 sine y cosine y, if you use this identity. So we could replace this with sine of 2y if we wanted to. That's not necessary, but I will say if you check your answers in the back of the book, they might actually have this because this would save some ink. Okay? All right, so I think with these examples, that's probably enough to get you rolling on the homework. And I will catch you all in the next one. Cheers.